Hi, my name is Ken Rasmussen. I wrote my microbiome prescription. By training, I am a statistician. I worked professionally for a number of years. And today is going to be a short technical note on detecting dysbiosis by using a very old classic statistical methodology, which is non-parametric, called chi-square. A reader basically dropped me an email this morning and asked, because his chi-square score was very high, probability of being significant was 1.0, and considering that I calculate the probability up to something like 8 or 9 decimal places, we can assume it is pretty significant. So the question is, he asked, does that cause a change of treatment plan? Well, the simple answer is no, it doesn't. It does indicate the person has dysbiosis, which is not a surprise because if somebody is doing a microbiome test, usually you can almost assume a priori that they have dysbiosis to begin with. The purpose of the test is basically to give a measure to see if the dysbiosis will decrease even marginally over time. And as it does, I've seen somebody with 0.9 with 8 nines or with 6 nines on subsequent tests go to 0.9 with only 3 nines, in which case that's improvement. Still have dysbiosis, but it's not as severe. Now the question is, how do you measure dysbiosis? There are a bunch of existing measures out there to measure dysbiosis. And if you check the literature, none of them work consistently well. They work for a few conditions. I mean, shown to work for a few conditions sometimes, but other times it fails. And we'll see that a little bit later down in this blog post. But basically, being a statistician, I try finding is there an easier way of doing it? Well, it turns out that there is when I started to look at things in terms of percentile. So, if you take a look at a particular taxonomy rank, let's say genus or species or strain or family, and calculate the percentile representation against the reference set, then basically, if you're looking at, let's say, 10 percentile, you expect in a true, typical non-dysbiosis scenario for 10% to be in each 10 percentile group. Simple as that. And now that you have your expected value, 10%, and you can go and compute your actual value for a particular sample, then you have expected and actual, and now you just walk through and do the chi-square formula and see what probability there is for just being random or just indicating dysbiosis. That is, there is abnormal shifts in the bacteria which are statistically significant. Very simple, doesn't apply to any and every condition, very straightforward to calculate, and the only thing you require is to be able to have percentile rankings against the reference population. With that, everything else becomes a very easy calculation. Basically, we would expect 10%, and I end up with a genus mainly because there are more genuses than there are families. And if you go down from genus to species, you probably get a better number, but I figure a genus is a reasonably good level. There's enough genuses involved. One can do it as species too, and the results are similar. Originally, I did both, and there was generally not much difference between the results from one or the other. So I said, okay, let's keep it simple. Let's work on genus level. So we do expect, here we have the red line being what we would expected value, which is 10 all the way down. And you can see that in the 0 to 9 percentile, it is underrepresented. In other words, there's not as many in this percentile range as would be expected, and then we go up and then we bounce back and forth. But where you really see it is the number of bacteria where you are at a very high amount compared to all the reference sets of it, and you have probably in this case you have almost double the amount of bacteria which are sitting at 90 percentile or higher, which means, okay, here's the dysbiosis, here is where it's likely happening, and if you take a look below, you have 24 candidate bacteria. So figure 12 of them would probably occur by random, and 12 of them are of concern. Unfortunately, we don't know which one of those two sets of 12 we really want to pay attention to, but we do know there's a problem. We do know there is dysbiosis, and we have a statistical measurement of how much dysbiosis it is, so we can come back after our intervention and see whether things have improved or not. Okay, as seen above, we have a number which are too high. We don't know which bacteria of the 12, actually 24 bacteria, 12 and 12 here is too high. So, but we know there's probably 24 bacteria which are massively overgrown, but we don't know which, so we cannot generate suggestions based on these. Generally, it becomes a bit tricky, but we at least have a short list of 24 bacteria, which are likely the ones which, if they are high, we want to focus on. But half of them are going to be false positives, and half of them are going to be true positives in terms of wanting to alter to normalize the dysbiosis. Now, if you look at some of the other measurements commonly used in microbiology, like the Shannon index, and do a bit of checking out, you find that some cases for some diseases there's no significance finding. Other cases it is, and generally it a little bit of hit and miss whether or not it works. And that applies to all of the different alpha diversity and beta diversity indices. When you check the literature, they work for certain scenarios, other scenarios they don't. Personally, I prefer one that should work for every scenario, and which is very rigorously gives us the probability of dysbiosis very precisely. Actually, even gives us a hint of which ones you want to pay a great amount of attention to, and which ones, in terms of being too low, you want to encourage. So I view it as a superior part to get a single measure of how much dysbiosis it is, and to see whether or not interventions decreases the dysbiosis, because you can just look at the p-value, and if the p-value decreases even a little, you know the intervention probably has been beneficial. So with that, I'll shut up and have people go to it.